Hi everyone, welcome back. Um, Hi Andrew, thank you for being with us today.
Hello.
How are you?
Doing just great and happy to be here, guys.
You are from Russia, right?
Yeah, Voronezh, Russia.
And how are things there?
Well, I think just like in any other country, people are going kind of crazy, being locked up in their homes.
Mhm.
But on the bright side, our bears have drank all the vodka that we had. So no more alcohol in Russia.
Yeah, maybe that will help killing the thing, right?
Hopefully.
Are you ready to start, Andrew?
Yeah, sure.
Okay, thank you. It's up over to you now.
Cool. So, once again, hello, guys. My name is Andrey Goncharov, and I'm broadcasting from my dad in the motherland of balalaikas, bears, and hackers, Russia. And today we're going to talk about lifting state up in our React applications and how that might affect the performance of our applications. But before we dive in and proceed to the technical side of things, let me say a few words about my company and about me. So, who am I? I like calling myself a full stack TypeScript and JavaScript developer, and that means that I've done a fair share of front end projects on React, Angular, even AngularJS, and some older stuff like jQuery, maybe any other overhyped as usual on the front end thing. And on the back end, it's primarily Node.js, but my experience is not limited to Node.js only. Whew. Going further, my career path can be visualized as going from two software consultancies, pretty significant in Russia, and now I'm happy to be a part of the family at Hazelcast, doing everything related to JavaScript there. And I truly love open source. Now about the company. What do we do at Hazelcast? At Hazelcast, our primary product is a memory data grid. I know it sounds fancy, but in simple words, it's an enterprise super blazing fast cache. So when your monstrous enterprise SQL query doesn't fit um, your needs in terms of performance anymore, come to us and we'll cache it for you. And I just have to say that we are scalable, we are easily deployable, we are distributed. And for those of you who know the CAP theorem, we have data structures on both sides of this CAP triangle. We have AP and CP data structures. Um, we have cool enterprise features like near cache. Uh, the coolest thing is that we are open source and we have official support for dozens of clients for different languages. Whew. Now our PR department is not going to put a bounty on my head and I'm not going to lose my life and my job. And we can go further to the management center. That's actually the team that I'm working in. And well, like any distributed, self-respected distributed system, self-respectable, sorry, we have management center, which is a huge console that allows us to manage our spaceship called a distributed cluster. We do monitor some statistics, some data structure statistics, and etc. Blah 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 blah. So now we have that all covered, and let's talk about the history of how I came up with this talk, so you know the context. At one of our internal hackathons, I came up with an idea of displaying our cluster as a graph, a real graph with edges and vertices. And just so you can imagine the scale, we can have up to, well, it's hundreds of nodes, it's thousands of clients, and data is distributed in hundreds of partitions across those nodes. So We are talking about displaying tenth thousands of DOM nodes simultaneously. Well, it was a hackathon, and the demo went smoothly because nobody reveals the performance issues on the demo, right? You just take the sunny day scenario and you run it. And for me, that was a 3-member cluster, and I didn't have any performance issues at that point. However, after the hackathon, I decided to see what React is capable of and how many nodes we can truly make it render without any significant impact on the performance. And what's the most natural way to structure our state for stuff like this, for displaying some uh, state of some huge entity split across some small entities? Well, usually it's the most natural way to do it is by lifting state up. So we would have a state of our cluster somewhere up in our hierarchy, and then we would pass the state of each node of each client as props, and it makes total sense. So our plan for today is to build a simplified version of my problem. We're going to build a very simple data grid. We're going to lift the state up, create a naive implementation, refactor it using standard practices, see where it fails and why. And then we'll try to move our state down and see how it can affect the performance. Let's go to the IDE and do some coding. I have a small confession to make. I'm not that good at live coding, so I prepared a series of commits for you. And I'll just apply these commits one by one and overview what changed. And the initial setup looks like this. We have an app component with some state of the entire field. The state of that field is a two-dimensional array of size by size, field with undefines. Size in our case for now is 10. And for that field, we iterate over each row, and then we iterate over the field, and then we iterate over each row, and render a cell for each cell in that row. That cell accepts a content prop and a set content callback. We'll get back to what the set content callback does later. And in our case, for now, that content is going to be undefined for all cells. Now let's switch to the cell component. It accepts content and set content, and it just renders the content inside of the div. And once you click on the div, it sets the content of that cell to the checkbox string. So in the end, we are going to have a two-dimensional array of undefines and strings. Now let's see what it looks like in our browser. So here we have that two-dimensional array rendered as a simple data grid. We can click on the cells and we can have that checkboxes rendered. And to reproduce the problem that I had, well, imaginary problem, to be honest, let's increase the size of the field to 100, go back to the browser and try to do some clicking, click, and it's, well, there is a small lag. Maybe you don't see it over the video, so let me go to the performance tab and do some CPU throttling. After all, not every user is going to have a high-end CPU, right? And some of our users, some users of our applications, and I'm not talking about our management center specifically, could use cell phones, smartphones, and they are definitely not going to have the same performance as my top shelf CPU has, right? So once we have throttled the CPU, let's do some clicking. Click, and it's rendered only now. Click, and it's rendered only now. So it's now the problem is obvious, right? You can go and grab a cup of coffee while React renders the cell. Um, and at this point, we really need to understand why this is happening. And to do that, we need some way to profile that thing. And the most naive way to do that would be, oh, sorry, next, to be add a simple console log statement. Sorry, let's go back to the code. So the only thing that changed here is that we added that console log. We all remember that a React component, React functional component, is just a function which gets executed on each render. So when we add that console log statement, we're going to have that statement displayed in our console on each render, and that would allow us to easily count how many renders of that component we have in our application. Now let's go back to the code and just notice that we have size equal to 10 again. So it's 10 by 10 two-dimensional array and 10 by 10 grid. And you can see that initially we have 100 cell renders, which is just fine because we are drawing the grid from scratch. And now let's do some clicking. A funny thing, when you click on a cell, another 100 cell renders occur. And that's not a very good sign, and that's not what we want. We don't want to re-render the entire grid when clicking on a single cell. What can be done here? And the most obvious thing, the most obvious way to fix it would be to go with what React suggests itself in our console. It says right here that each child in the list should have a unique key prop. So let's go back to our code and do exactly that. Next commit. So what happened now? Now you can see that we have a unique key for each row, and we have a unique key for each cell. Let's go back to our code and see if it changed anything. Once again, we start from scratch, from an empty grid. Click, and we still have the same 100 renders for each click. And now we have 500 renders in total for 4 clicks, which is not great and doesn't scale well. Luckily, um, React team provided us with a great profiler, which can help us with defining why some components render. So let's go back. Let's go to the profiler. Let's go to the settings and apply. Check that checkbox, record why each component rendered while profiling, and let's start a profiling session. Click, stop, display it as a ranked chart. And now we can see that, well, why this component rendered. And the profiler tells us that props changed, specifically set content. Let's go to our code and see why is that. So what's happening here? I promised you to go back to set content at some point, and now is the perfect time to do that. What happens here? When we try to update the state of our cell, we accept new content for that cell. In our case, that's going to be a string with that check mark, and then we call set field. In that set field, we copy all other rows but our target row that we want to update. We copy all other cells but our target cell in that row, and then we replace the content of that cell, of our target cell, in that row. And why does it change? The thing is that we use field from the outer scope, right? VS Code highlights it. So when a single cell updates its state, it updates the whole field. And then the set content callback is updated for each cell because the field from the outer scope is updated. Now let's try to eliminate that update. We need some consistent uh, function, some consistent callback that we pass to our cell to update the state of that cell that doesn't change over time. So a lot changed here, but don't worry, we'll go over it line by line. So let's start with the cell component as the easiest thing to do here. Um, we still accept content, but now we accept cell index, row index, and another new version of set content callback. And in that set content callback, we're going to pass that row index, cell index, and the new state of our cell. And the most interesting thing happens in that new set cell or set content callback. So what we do here is that we accept row index, cell index, and new content. Then, to eliminate that dependency on the field from the outer scope, we use a callback signature of the set field or set state callback. So as you might know, uh, our set state callback can accept new state in two different versions. You can either pass a new state as as a variable, as an object or as a primitive that you defined earlier, or you can pass a callback that's going to get an old version of that state that you can manipulate. And that's exactly what we do right here. We use the callback signature, which accepts the previous state. We use that previous state to do the same thing that we did before. We immutably copy each row besides but our target row. And in our target row, we copy each cell but our target cell. And for our target cell, we update its content. And we use callback helper provided by React to maintain a stable reference to our set cell callback. That should help, right? Let's go to our application and do some clicking. And still we have 100 renders for each click. But now you know the drill. We start the profiling, click, stop the profiling, rank chart, and let's browse through each cell render and see why was it rendered. And our React profiler tells us that the parent component was rendered. Going back to our code, what happens here? So with each field update, the set field callback is called. It updates the field variable. And because that variable is updated, our app component re-renders. So for each cell update, our app component is going to be re-rendered as well. But that's expected, kind of. What's not expected is that every cell is going to be re-rendered when our app component is re-rendered. We maintain a stable reference to our set cell prop. Our other props are primitives and they have the same value. So what we want here is that our cell component is no longer re-rendered with each re-render of the app component if its props doesn't change. Cool. How can we do that? In our case, we can apply memo, which is going to, well, kinda memoize our component, if you want to call it that way. So the bottom line here is that if props don't change, the component is not going to be re-rendered. Other ways could be to use um, pure component if you use class components or should component update. So once we have that memo in place, let's go back to our browser and see what's going on here. Let's do some clicking. And yay! We can see that every click is producing a single cell render. And now you gotta be asking yourself a question: why have I come up with this presentation with this talk in the first place? Because the standard way to optimize that kind of application works out of the box. And we have hundreds of great articles, including React documentation explaining that procedure on how to optimize renders for lists and etc. and etc. I suggest we increase the field size to 150. It's going to take quite some time first. We're almost there. And here we go. We have a huge field. And no CPU throttling. Let's try to do some clicking. Click. Click. There is a slight tiny lag that I see and you might not see. Let's do some throttling. And remember that not all of our users are going to have top shelf CPU. Click. Blah, blah. Click. 1 Mississippi, 2 Mississippi, 3 Mississippi. Click. 1 Mississippi, 2 Mississippi. So it takes on average between 2 and 3 Mississippis to render even a single cell when we have a huge grid of cells to display. Once again, profiler to the rescue. Hopefully it's going to answer the question why this is happening. Now we're re-rendering only a single cell. So what's going on here? Why does it feel so laggy? Let's start the recording. Click, stop the recording. And here we see a weird thing. The render of that very cell takes not so much time. Actually, it's crazy fast. It's 0.3 milliseconds. However, the time that takes to render the whole application is enormous 100 milliseconds. And that's exactly what we see. Why is that? Let's go back to the slides. So the reason why React succeeded, one of the reasons was that we tend to think that rendering DOM trees is crazy expensive. And then React came with its own version to its own its own version of how we have to do things to avoid that expensive real DOM rendering, and React introduced a virtual DOM. And we tend to think that virtual DOM is cheap. Rendering virtual DOM is cheap because it abstracts the real DOM manipulation, and it's cheap indeed. However, we have to remember that cheap doesn't mean free. What happens what happens there is that, let's go back to the code. We have a huge field, 100 fields by 100 fields. So it's, well, how many fields was that in total? 22,500 cells. And for every cell, React has to go and compare its props. It's pretty fast. We can see that uh, rendering a single cell with comparing its props takes only zero point 0.3 milliseconds. And we can assume that without rendering, just comparing the props of a single cell takes even less, significantly less, because it doesn't have to deal with the real DOM manipulation. However, it's still some time. It's not instant. And when you multiply even a tiny number, even a very small amount of time by 22,500, you get that 100 milliseconds. So now, if we cannot lift our state up, maybe we can do something else. Can we move it down? Next commit, and a lot has changed. But don't worry, we'll go over it line by line. Let's start with our cell. Now our cell accepts a cell index and a row index, and it use some mysterious cell content function from our field to get the content that we're going to render, and it use another mysterious set cell function to update its content. In our app component, we iterate over that field using map, and for each cell, in each row, we render that cell, passing the key, row index, and cell index. That field is an instance of the field class that accepts size as its only parameter in the constructor. And now the most interesting thing, our field class. So our field class accepts field size in the constructor, and in the constructor it creates the same two-dimensional array. It's basically copy-paste from the initial state from the previous commit. The cell content callback just returns the data from our two-dimensional array. It's just a way to encapsulate that data. Our set cell is basically copy-paste from the old set cell callback that we had. It's the same thing, we copy each row, and in our target row, we copy each cell and update only our target cell. Cool. And we have a map method to iterate over that two-dimensional array. So the main thing here is that now our field lives outside of the React. So React doesn't know what's going on with that field. So you can imagine it like having some React scope on one side and field somewhere else. And React uses that field just from the outer scope. Let's go to the browser and do some clicking. And you can see that we have some set cell console log statements, but we have nothing displayed on our screens. Why is that? As I said, now React doesn't know what happens inside of that field because, well, it's just a variable from the outer scope. And we have to somehow let React know that that variable is updated and React has to re-render. Next commit. What are our options to trigger a component re-render. We can update the component props, which is going to trigger the re-render of that component. However, that would defeat the purpose of our optimization. We try to avoid changing props at all costs. Another thing that we could do is to use force update if we use class components. However, here we don't use class components, and I'm not willing to rewrite my entire application to class components. And one last thing that we could do is to update the state of our component. And that's exactly what could help us here. We are going to use a custom hook, use force render, which is going to just increase a counter, leaving an out state by 1 every time we want to trigger an update. In our case, we use a use reducer signature, and you can see that every time we call that force render function, we're just going to increment the state of our reducer by 1, starting from 0. Now that we know how to update the cell, how to trigger that force rendering, we need to somehow know when to trigger that. And to do that, we're going to subscribe to cell updates of that field. Let's take a close look at that simple method. It accepts row index, cell index, and some callback that's going to be called when the subscription should be fired, executed. In our constructor, we introduce subscribers object. And when we subscribe to a certain cell update into that subscriber object by a certain key, we place that callback. Let's head to that internal method, cell subscriber ID, and we can see that it uses row ID and cell ID, and it concatenates them in a string. Another change that we have is that we now have to call that subscriptions when we update our cells. So in our set cell, we try to find a suitable subscription from our subscribers object. And if a suitable subscription for that row index and cell index is found, we execute that callback. So basically, we notify our subscriber that a certain cell is updated. In our cell component, we still accept the same cell index and row index. Now we use our brand new custom hook use force render to get that force render function to increment the state of that integer, to increment that integer. And using use effect, because it's a side effect, we subscribe to our cell updates, passing the row index, cell index, and that force render. So now when the cell, our target cell, is updated, the force render function is going to be called. The integer is going to be incremented from 0 to 1, from 1 to 2, and etc., and the cell should be updated as well. Let's go to our browser and see if it works. Click, click, and we can see that we have check marks in place and we have all necessary console log statements in place. And just to make sure that it truly works at that scale, let's go back to our code and increase the field size to 100 all over again. It's a perfect time to grab a cup of coffee. I wish I knew some anecdotes to tell while this grid is rendered. Okay, now we have 22,500 components, and let's do some clicking. Let's click on some of those cells. At this point, it's blazing fast, but we all know that the thing might not be what they appear to be. Let's do some CPU throttling to account for cell phone users and old PC users. Click, and it's still pretty fast. Click, click, fast, click, click, click. And I want to raise my hands in this victorious gesture. Seems like we have defeated the culprit that prevented us from having a super performant, infinitely scalable data grid. And just to make sure that everything goes as expected, let's head to our profiler and do some profiling. Stop. Yay, now we can see that we no longer have that enormous app re-render that took 100 milliseconds. With each click, we re-render only that very cell. Let's do some profiling all over again, do some more clicking. And we can see that for every click, we have a different commit, and we have a different cell rendered, and that only that cell is re-rendered. And last but not least, let's head back to our IDE and apply one last commit. Because you have to remember to unsubscribe every time you subscribe to something. Otherwise, you're facing some memory problems. So now we introduce unsubscribe cell updates, which removes that callback from that huge object. And in our use effect, we return an unsubscribe function, which unsubscribes us from that cell updates. Let's see that we didn't break anything, and we didn't. Cool. And back to our presentation. Closing words. Don't do any premature optimizations. I mean, really, really don't do it. Because as we saw, well, it's a way to work around the problem. But first, you have to ask yourself a question. Do you really have a problem in the first place? And by saying it, I mean, uh, do we really need to render that huge data grid? Or is it just an imaginary problem that your engineer shaped mind came up with? Because most applications, I would say 99% of the applications would do just great using standard practices. Because, well, we saw that these practices work on a pretty large scale. And even with this data grid, if we had a field of size, say 50 by 50, we would probably be better off with using the standard practices. However, you should always remember that rules are meant to be broken, and if you have a good enough reason to break a rule, just don't hesitate. Go ahead and break it and share your experience with other people, with other folks. Maybe someone else is suffering from the same problem. And one other thing, I'm not saying that this implementation is a reference implementation of how you should move your state down. There are great libraries to do that, and I have not used them personally, but um, as far as I know, Mobax does exactly that. So it places your state outside of your React tree, and you subscribe to only that pieces of the state that you need. And I'm pretty sure that uh, there are other libraries, other great libraries that would help you with moving your state down. So consider this as just a way to maybe extend your horizons and think all over again on about how React does its rendering and that nothing is really free in this world. Um, in this presentation, you'll find the links to the related article and to the repo with the source code. You can contact me in any way you want using Twitter, Telegram, email. Here's the QR code to this presentation, and happy to be here, guys, and happy to share this afternoon with you speaking about React. This is it from me. Any questions?
Thank you for being here, Andrew. So yes, we have some questions for you. If you have other questions, guys, please ask them on YouTube live stream or in the Slack channel. So before that, a comment from Alejandro. Great presentation, Andrew. And Michael says that he was looking for this. So that's amazing. A question we have is, I want to understand correctly. By default, React don't do it right, or we just can do it better.
By default, React provides us with a great way to approach that problem, and I think that React by default does it 100% right. It's just a workaround, well, another way to approach the problem at scale when you have a really, really demanding in terms of rendering component. That's it. And even if not that, maybe just a way for you guys to remind yourself about the trade offs, about the price that you pay for each optimization and for each engineering abstraction.
Let's see if we have another question. So we don't have any other question for now, Andrew. If you want to ask Andrew a question, maybe leave it on Slack, and if Andrew can join us on Slack, maybe we can answer it later.
Yeah,
So,
sure. Sounds like a great
or
way to do it. Or
yes,
you can tweet me, guys. Just everybody's on Twitter, right? So just
yeah.
use Twitter.
Okay, so before you go, just one last question that was asked just now. In your example, each square was representing a component, right? And you were optimizing the way the state is updated, uh, uh, and you were optimizing the way the state is updated. Is that correct?
Well, yeah, yeah. We had we had thousands of components, and we just tried to optimize how we update the states of that components. Yeah.
Yeah. Okay. Thank you, Andrew, again. Nice to have you. Hope to see
Thank you
you
for
again
having
in the
me.
future. See you.
Yeah.
Bye. Thank you all.
See you guys.